Chapter 8 Non-electrolyte Solutions Section 8.9 Activity. In an ideal solution, the chemical potential of each species can be calculated using this equation. The chemical potential of species I in the ideal solution equals the chemical potential of pure I plus RT, natural logarithm of the mole fraction of I. Star denotes pure. For a real solution, we need to modify this equation. We just need to replace the mole fraction X with the activity A. So now we have this equation. The chemical potential of species I in a real solution is equal to the chemical potential of pure liquid I plus RT times the natural logarithm of the activity of species I in that solution. So now why activity? So activity may be viewed as the effective mole fraction. However, it's more than just the mole fraction. In activity, the intermolecular interactions is taken into account. Alright, so in a real solution that consists of two components, let's say A and B, the interaction between A and B, the interaction between A and A, and the interaction between B and B can be different from each other. And in this activity A, the difference is taken into account. It's very difficult to determine the activity of species I in a solution directly. Instead, we actually just measure the vapor pressure of this liquid I on top of the solution. When a real solution is at equilibrium with the vapors at given temperature and pressure, if we can assume the ideal gas behavior of the vapors, and then we have this equation. First, at equilibrium, the species I over here in the solution and the species I in the gas phase, they have the same chemical potential at equilibrium. And over here, the chemical potential of species I in the gas phase is equal to the chemical potential of pure I in the gas phase plus some correction over here. The correction is RT times the natural logarithm of Pi over Pi star. Again, Pi star denotes the pressure of pure liquid I. And over here, that's the chemical potential of the gas phase above pure liquid I. When the liquid and gas phase of pure I are at equilibrium, we have this equation. Again, this star means pure, and we have species I, and we have the chemical potential of the gas phase equals the chemical potential of the liquid phase. And therefore, we have this equation. Again, the species I in the solution is equal to, over here, we just have this part replaced with this part. Now we have mu sub I star liquid plus RT times the natural logarithm of Pi over P star. So essentially we copied these two terms right here, and we replaced this term with this term, because when the liquid and gas phase of pure I are at equilibrium, we have this equation. Therefore, this is equivalent to this. Now let's look at this equation and this equation. This equation comes from the definition of activity. You can see we have mu star liquid for species I that appear on both sides of this equal sign. So these two may cancel, and then RT and RT cancel, And then we have A sub I equals Pi over Pi star. So now we can determine the activity of a liquid component in a real solution. It's simply Pi over Pi star. We need to measure the partial pressure of this species I on top of the real solution, and then divided by the vapor pressure of pure liquid I. That's gonna be our activity of this species I in a real solution. Of course, in an ideal solution, you can see this Pi over Pi star is simply the mole fraction. Therefore, in an ideal solution, the activity equals the mole fraction. Again, for ideal solutions, the activity of component I is simply A sub I equals Pi over Pi star equals X sub I. Again, A and X are the same for ideal solutions. But in an ideal dilute solution, it's going to be a little bit different. The activity of the highly diluted component I is determined with a hypothetical state of I. So what's this hypothetical state of I? Each solute I is surrounded by 100% solvent molecules. Again, this is just hypothetical. So it's highly diluted. So mostly each solute molecule is surrounded by mostly solvent molecules. We just need to extend it a little bit, hypothetically, to 100%. And that's used as a reference. So in this case, for the solute, in an ideal dilute solution, we actually use this Henry's constant as the reference. So the activity of the solute is equal to the partial pressure of species I divided by Henry's constant. And again, in an ideal dilute solution, this is simply the mole fraction of I. So AI is equal to Xi for the solute in the ideal dilute solution. Here's the example when the mole fraction and vapor pressure of a species in an aqueous solution are 10 to the power of negative 5 bars, and over here 2 times 10 to the power of negative 5 bars, and then its Henry's constant is simply over here we have this equation coming from this equation. Henry's constant is P sub I over A sub I. Again, we just rearrange this equation for the activity of the solute in an ideal dilute solution to determine the Henry's constant. It's Pi over AI, and in an ideal dilute solution, AI is approximately Xi, and then we plug in these numbers. The Henry's constant is 2 bars. In such a highly diluted solution, for both the solvent and the solute, we have A sub I is equal to X sub I. However, remember, for the solvent and for the solute, we use different references. The ratio between the activity and the mole fraction of a liquid component in a solution is called activity coefficient. This is denoted by gamma. Gamma is just the activity divided by the mole fraction. Gamma equals 1 for both solvent and solute in an ideal solution. Alright, that's just pretty simple there. In an ideal dilute solution, the situation is slightly complicated and a bit confusing, because in an ideal dilute solution, look, each solvent is surrounded by 100% other solvent molecules, and each solute is surrounded by also 100% solvent molecules. So we are kind of using a different standard here. In highly dilute solutions, different standard states are used. So when the mole fraction of the solute approaches 0, its activity coefficient approaches 1. For the solvent, when the mole fraction of the solvent approaches 1, the activity coefficient approaches 1. So you can see we have 2 different limits over here. Over here, we're assuming the mole fraction of the solute is close to 0. Over here, we're assuming the mole fraction of the solvent is close to 1. But anyway, this case and this case together is reflected by this ideal dilute solution. In ideal dilute solution, the gamma value of the solute is 1. The gamma value of the solvent is also 1. Now let's look at a general chemical reaction from A plus B to X plus Y. If we have an ideal solution, the equilibrium constant of mole fractions is simply K sub X, and we have products on top, reactants on the bottom, and we use the mole fractions of X and Y on top, raised to the power of the coefficients, stoichiometric coefficients. And then on the bottom we have A and B, those are the reactants. We have the mole fractions of A and B raised to the corresponding power as well. And then over here we specify the equilibrium condition. That's really simple for an ideal solution. However, if we have the same reaction in a real solution, the equilibrium constant of activities is this. K sub A denotes activity. It's the activities of X and Y on top raised to the power of the stoichiometric coefficient. And on the bottom we have reactants A and B, and we have the activities of A and B. And because A is X times gamma, gamma is the activity coefficient, X is the mole fraction, so we have a product of these two terms. This term is the same as this term, but we need some correction over here. The correction is due to this activity coefficient not being equal to 1. Why do we need this? Because in a real solution, we have the standard Gibbs energy of reaction is equal to negative RT times the natural logarithm of the equilibrium constant of activities, not of mole fractions. It's of activities, because in the activities we take the interactions between AB, AA, and BB into account properly for a real solution. In essence, activities are the effective mole fractions that take into account the change in the intermolecular interactions upon mixing. Again, if we have two components A and B in a real solution, the AB interaction is different from AA interaction. The AB interaction is different from the BB interaction. Therefore, upon mixing, well, each molecule in this solution is feeling a different amount of attraction or a different amount of intermolecular interaction. So we need to take that into account in the Gibbs energy. For real solutions, we can use the following equations to determine the activity of species I in the solution relative to pure I. Over here we have this equation: A sub I is equal to P sub I over Pi star. We're assuming ideal gas behavior of the vapors. P sub I is the partial pressure of liquid I on top of the surface of the solution. P sub I star is the pressure of pure liquid I. And again, we're assuming ideal behavior of the vapor of I in this equation. Now, what if they do not behave ideally in the gas phase? Well, then we just need to use the fugacity of I on top of the solution divided by the fugacity of this I on top of pure liquid I. Again, there's an exception for the solute in a highly dilute solution. We're not using Pi star on the bottom. Instead, we use Henry's constant as the standard state. So in this case, the activity of the solute in a highly dilute solution, or we can say nearly ideal dilute solution, the activity is equal to P sub I over Henry's constant. we use this equation to determine the activity for the solute in a highly dilute solution. When the mole fraction of the solute approaches 0, its activity coefficient approaches 1. And at the same time, we have the mole fraction of the solvent approaches 1, and the activity coefficient of the solvent also approaches 1. When the activity coefficient approaches 1, the activity approaches the mole fraction, because the definition of the activity coefficient gamma is simply A over X. When gamma approaches 1, A approaches X.